Okay, another model we'll look at, spread of a disease, contagious disease, for example, the flu is spread throughout a community by people coming in contact with other people. So let's let x of t denote the number of people who've contracted the disease, and y of t denote the number of people who've not yet been exposed. Seems reasonable to assume the rate at which the disease spreads is proportional to the number of encounters or interactions between these two groups of people. If we assume that the number of interactions is jointly proportional to, and that is proportional to the product, then dx dt would equal k, that constant of proportionality, xy, where k is the usual constant proportionality. Suppose a small community has a fixed population of n people. If one infected person is introduced into this community, then it would be argued that x of t and y of t are related by this relationship here of the people who have the disease and the people who don't have the disease add up to n plus 1. So using this equation to eliminate y, we get the model of dx dt equals k x of n plus 1 minus x. Okay. And we can assume, I'll let you kind of chew on that for a second, that x sub 0 has to be 1. That's an assumption we can make when we're doing this particular type of problem. So kind of think about that. Why would our initial x have to be 1? Well, if x measures the number of people sick and we're trying to spread disease through a population, then we have to assume that there does exist a sick person. Otherwise, this formula is very boring, and no one would get sick if there wasn't a sick person there, if that makes sense. All right, so let's take a look at an example. Suppose a student carrying the flu virus returns to an isolated college campus of 1,000 students. Determine a differential equation for the number of people x of t who've contracted the flu if the rate at which the disease spreads is proportional to the number of interactions between the number of students who have the flu and the number of students who've not yet been exposed to it. Okay, so according to this model, how many students have the flu? So we have number have, let's just do number of flu. Okay, so according to our model here, what would we express the number of people who have the flu with? That would be x. So the number of people who don't have the flu, so we'll do complement for that. That would be, let's see, there's 1,000 people in this particular population, so that should be 1,000 minus x. And so dx dt is proportional to the product. So that would equal k x times 1,000 minus x. Yay! Suppose a large mixing tank initially holds 300 gallons of water in which 50 pounds of salt have been dissolved. Another brine solution is pumped into the tank at a rate of 3 gallons per minute. When the solution is well stirred, it is then pumped out at a slower rate of 2 gallons per minute. The concentration of the solution is entering at 2 pounds per gallon. Determine a differential equation for the amount of salt in the tank at time t. Okay, so let's see if we can get sort of a simplistic picture here. We have a tank, and we have water and salt already in the tank, right? 300 gallons of water, 50 pounds of salt. We are pumping in a certain brine solution. So there's a rate at which it's going to come in, and then we're also pumping out at a different amount the solution. So over time it's going to change, and we'd actually expect the salt concentration to actually get bigger because it's going out at a slower rate. Okay. So let's, just so we are all on the same page here, let's say A is the amount of salt. Okay, and so dA dt is the change in salt over time. Okay, so in a very simple equation, our change in salt over time is going to be the rate going in minus the rate going out. So that's a simplistic model, right? That could work, but we can do a better job because we have enough details that we can fill in some blanks here. So let's talk about the rate of the salt coming in. So rate going in. Okay, well, what do we know? We know that this brine solution is coming in at 3 gallons per minute. And we know that the concentration of solution is entering at 2 pounds per gallon. So that calculation there can give me a quick conversion of how many pounds per minute of our salt solution are accumulating going in. So we'll divide out our gallons. That'll give me 6 pounds per minute. So over time, the salt solution going in is increasing things at 6 pounds of salt per minute. Okay, what about the rate going out? Okay, so let's kind of think real quick about when it's leaving, right? We're pumping in at 3 gallons per minute. We're pumping out at 1 gallon per minute. So at 3 minus 2 gallons per minute, right? So that means the salt is going to be accumulating 1 gallon per minute. Right? And so if we said that there's 300 gallons in the initial, then over time we're only adding 1 gallon per minute. So each minute we're just going to add T gallons to the mixture. So over as time goes on, then our amount of salt is going to increase by 300 plus T. Right? So our rate, we said the amount of salt was A, and then over time it's going to be 300 plus T. So that would mean our rate going out is the 2 gallons per minute that we have the valve set on, and then we additionally have that salt accumulation increasing at A over 300 plus T pounds per gallon. Right, gallon per minute. So the gallons are going to divide out, and that's going to give me 2A over 300 plus T pounds per minute. So you tell me how long the process starts. You tell me how much. Initially, I can fill in some numbers there, and there we go. So our rate then, the differential equation that would describe the amount of salt at time t, would be that initial 6 that we found minus this 2a over 300 plus t. So we could plug the 50 in there, and that could give us a nice pretty number to go with, or we can just leave it in the general sense there. So anyways, there is that differential equation for us.